Hi everyone, this is Infinity YouTube channel. Please remember to like, subscribe and share. Alright, so today we are going to work on the transformation of the derivative of f of t. So far we've been working on the Laplace transform and we've worked on the inverse of the Laplace transform. So today we are going to work on the transformation of the derivative of the f of t. So remember from earlier on, I told us that one of the importance of Laplace transform is that the Laplace transform helps us to analyze the circuit, okay? It helps in the analysis of circuit. That's one. The Laplace transform, on the other hand, also helps to analyze mechanical vibration, okay? So we are going to understand how we can transform these f of t's when in their derivative. So the Laplace transform as well helps us to solve the ordinary differential equations, and it helps us to solve equations like the simultaneous equations and so on. So there are many usefulness of the Laplace transform. So just pay attention and see how we can easily decipher and make use of the Laplace transform in solving equations, especially the ordinary differential equation as for this video. Alright, so from what we know earlier on, we know that if the Laplace of f of t, that if the Laplace of f of t is equal to the f of s, as we already know, that if the Laplace of f of t is equal to the f of s, which means that the Laplace of the derivative of this f of t, which is the f of t dt, will now be equal to s f of s minus f of 0. So this is a standard that you should know. So the standard that you should know is that when you find the Laplace of the differential of f of t, what you are going to have is s f of s minus f of 0 as your answer. So let's go further. What if this is for the first derivative? What if you want to find the Laplace of the second derivative, the Laplace of the third derivative, the Laplace of the fourth derivative, up to the Laplace of the infinite derivative? So let's go. So let's say you want to find the Laplace of the f squared f of t dt squared, right? What if you want to find the Laplace of the second derivative? So the Laplace of the second derivative will be equal to s squared f of s minus s f of 0 minus f prime of 0. So before I continue to write further, mind you that the f of t dt can also be termed as y prime. This is the same thing as saying the Laplace of f prime of t. Laplace of f prime of t. So this one as well, instead of saying the squared f of t dt squared, you can also replace this by saying f prime prime of t, Laplace of f prime prime of t. Are you there? So in writing the third differential now, I will not be using this way, I will just be using these denotions, right? So that means the Laplace of f prime 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 of t now will be equal to, that is the Laplace of the third differential, will now be equal to s cubed f of s minus s squared f of 0 minus s f prime of 0 minus f prime prime of 0. Now I'm going to write for the fourth derivative, but I will show you the same hierarchy that they are following. Alright, the same chronological order. So if the Laplace of f to the fourth differential of t is equal to s to the fourth f of s minus s to the cube f of 0 minus s squared f prime of 0 minus s f prime prime of 0 minus f prime 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 of 0. Alright, so this is the same way, it follows the same pattern up to the infinite differential. Are you there? So let's look at this pattern and let's see how this pattern works, okay, so that you do not need to cram it for study purposes or for exams purposes. Now when you had the first differential, what the power of the s was 1, right? Then just know that f of 0 is always constant for all of them. Alright, let's go. So as you are trying to decrease the s, the f is increasing. So initially the s was just to the first power, but looking at the s here now, s is to the 0 power. Then f of s was at neutral, but now it has just increased to f of 0. Are you there? Let's check the second one. When it was the second differential, as you can see that the s squared showed that it had the second differential, f of s. So looking at this, now you can see that the power of s kept on reducing from 2 to 1 to 0, and the f kept on increasing from f of s to f of 0 to f prime of 0. So the third one now, the same thing, the s kept on reducing, q s to the third power, to the second power, to the first power, and to the 0 power. As well, the f also increased in its differential. Likewise, the fourth differential. Alright, so this is just the pattern that you can easily decipher the Laplace of the derivative of the f of t's. So we are going to employ this knowledge of the Laplace of a derivative to solve the ordinary differential equation, especially when the initial condition is being given. Are you there? So let's go through an example. So let's say that we have to determine example 1. Let's say we have to determine the solution of the following. Determine the solution of the function of the equation. Determine the solution of the equation. The solution of the equation. Alright, so we have dy dt plus 3y is equals to the exponent of minus 2t. Given c equals 0 and y of 0 equals 2. Alright, so this is a simple example that we are going to use to understand how we can use the Laplace transform to solve the ordinary differential equation. As you can see, this is a differential equation, so we are going to use the knowledge of Laplace to do such. Alright, so now let's go. So the first thing you have to do from here, is to you may decide to rewrite this dy dt as y prime, because dy dt is the fourth differential of y. Alright, so dy dt here means y prime plus 3y is equal to the exponent of minus 2t. Alright, let's continue. So the next step we have to do is to find the Laplace of both sides. That means the Laplace of the left hand side and the Laplace of the right hand side. So if you should do that now, we are going to find the Laplace of each of these functions, right? So the Laplace now of y prime will be equal to, now let's do a comparison. Y prime is like saying f prime of t, right? They are just the same. Y prime is like saying f prime of t. So the inverse Laplace transform now will be s of ys, s of ys minus y of 0, right? If you find the Laplace of it, just the same thing. The only thing I had to do was to change the f to y because we are dealing with a y function. Now, if you find the Laplace of 3y, look, mind you, before we go ahead, mind you, let's assume that a number was in front of this. Let's say 2y prime. So if there was a constant like 2 in front of the y prime, after you found the Laplace of that y, always remember to multiply everything by 2. Alright? The 2 will be distributed to the answer to the Laplace that you found. Alright, so have that in mind. Let's continue. So now that you have Laplace of 3y, what we have to do is, one of the criteria, one of the functions of a Laplace is that a constant can easily come out of the Laplace, just like an integral. Alright, so if the constant comes out of this Laplace, it means 3 into the Laplace of y. 3 into the Laplace of y. And Laplace of y is It's like saying the Laplace of f of t. Are you there? So Laplace of that f of t, which is equal to the f of s, is equal to y of s. Alright, now remaining the last one, the Laplace of exponent of minus 2t. Right? So the Laplace of exponent of minus 2t from so far we've done will be equal to 1 divided by s plus 2. Right? If you find the Laplace of exponent of minus 2t, you are going to have s plus 1 over s plus 2 as the answer. Alright, so since we have all these functions, what we have to do now is to impute these functions back to the original equation. Alright, the Laplace of each of them. Now let's go on. For the sake of this video, let us just say that y of s should be equal to just y. Okay? Let's just say y of s equals to y because of the sake of this video. Now let's continue. Now this will now be equal to, instead of writing y prime now, I will take s of y minus y of 0 plus 3y of s. So remember, when you use 3 to find the Laplace, always put 3 as well on the function. So let's go. So you have 3y is equals to 1 over s plus 2. Right? This is what you are going to have. So the next step you are going to do is to look at the initial conditions that we are given. So judging from here now, the initial condition was that y of 0 should be equal to 2. So wherever we see y of 0 in this function, we should make it to be equal to 2. Alright? So this will now give us s of y into minus 2 plus 3y is equals to 1 over s plus 2, which you can easily take the 2 over. So when we take the 2 over here, we have s of y plus 3y is equals to 1 over s plus 2 plus 2, right? So this is what we are going to have. Now, if you add 1 over s plus 2 plus 2 together, what you are going to have will be s of y plus 3y will now be equal to 5 plus 2s divided by s plus 2, right? Whenever you add these together, you are going to have 5 plus 2s divided by s plus 2. Alright, so let's continue. So the next we are going to do is to factor out the y from your left hand side. Factor out the y. So when we factor out this y now, we have y into s plus 3 is equals to 5 plus 2s divided by s plus 2. Alright, so this is what we are going to have. So the next step we are going to do is to multiply both sides by 1 over s plus 3 because I want to make y to stand alone. Okay, I want to make y the solid of the formula. So to do that now, if I should multiply both sides by s plus 3 now, I have y is equals to 5 plus 2s divided by s plus 2 into s plus 3. Alright, so if you don't want to multiply both sides by 1 over s plus 3, you can simply say cross multiply, right? Just cross multiply only s plus 3 and to multiply s plus 2 down, right? Leaving only your y on the left hand side. So, but whichever way, when you make y the result of the formula, this is what you are going to have on the function. So, but the question we are going to solve here is not to find y, right? Is not to find y. So, is to find, is to decipher this, right? Is to decipher this and find the y of t eventually. Alright? So, how can we get the final answer to this y? How can we get the final answer to this y and find the y of t present? So, what we'll do is to separate this function. We should separate it, right? So, one of the mathematical approach to do such is by using the partial fraction. So, but let's just go through the use of the partial fraction step by step and see how the partial fraction can help us to separate this function in the equation. So, a little recap on the partial fraction says that if you have this type of function, this is simply equal to a over the first denominator, which is s plus 2, plus b over the second denominator, which is s plus 3, right? So this is what we are going to have. Alright, so remember when doing a partial fraction, don't look at the numerator when you are trying to separate the a and b together. Just look at the denominator and impute them under the a and the b. So the next thing you are going to do is to multiply a by the denominator of b and multiply b by the denominator of a. Alright? So if you do that, what we are going to have is a into s plus 3 plus b into s plus 2. So when you have gotten that, this should be equal to the numerator of the normal function that you were doing. Alright? So what you are going to have now is 5 plus 2s. Alright, so the next thing we are going to do is to eliminate a and b in the equation. So you are going to eliminate a first or b first, whichever one you want to start with first, and then you go ahead to eliminate the other. So let's assume I want to start with a. So if I say let s equals minus 3. If s is equals to minus 3, I can see if I put minus 3 here, a goes to 0, right? So what I have left will now be b into minus 3 plus 2, which is equals to 5 plus 2 into minus 3. So this is what I have. And minus 3 plus 2 gives me minus 1. And minus 1 times b gives me minus b, which is equals to 5 plus 2 into minus 3 gives me minus 6. So that means 5 minus 6. And of course, this gives me minus b, and 5 minus 6 gives me minus 1, which means that b is equals to 1. Alright, so since you are putting b as 1, the next we have to do here is to eliminate b. Alright, so to eliminate b now, we can see let s equals minus 2. So if s is equals to minus 2, if I put minus 2 into this b, you can see that b can easily go to 0. So what we have there is only on a and on the right hand side. So we have a into minus 2 plus 3, which is equals to 5 plus 2 into minus 2. Alright, this is what we are going to have. And minus 2 plus 3 gives me 1, and a times that 1 gives me a. Alright, so I just have a here, which is now equal to 5. Now, 2 into minus 2 gives me minus 4. So I have 5 minus 4, which of course is equals to 1. Therefore, a is equals to 1 and b is equals to 1. That is to say that y, which was equals to 5 plus 2s divided by s plus 2 and s plus 3 now is now equal to a, which is 1, right? Divided by s plus 2 plus b, which is 1 as well, divided by s plus 3. Alright, so when we have this and this, so which f of t gives us this kind of function? Which f of t gives us this kind of function? We can clearly see that y of that t now, that y of t, which is the final answer, will be equal to the exponent of minus 2t plus exponent of minus 3t. So this is the final answer to this equation. Alright, so when we've separated the function, immediately we've separated the function, the next thing we have to do is to convert it to the f of t that function looks like. And that will give you the answer to the differential equation that was present. Alright, so we are going to go through another example, and then we are going to see how we can also utilize the idea of this inverse Laplace transform to solve the ordinary differential equation. Alright, so for the second example now, the second example now is thus as above. So we have that y prime minus y minus 6y is equal to 0, given that y of 0 is equal to 1 and y prime of 0 is equal to minus 1. So this question is just telling us that we should use the Laplace transform to decipher this differential equation. Alright, so using Laplace to solve this equation now, what we have to do is solution. So the first thing we have to do as usual is to find the Laplace of each of the function, right? Just find the Laplace of each of the function. And the Laplace of the first one, which is the y prime prime now, is s squared y of s squared y of s minus s y of 0 minus y prime of 0. Alright, so if you should find the Laplace of this is the answer we are going to have as is the Laplace of this derivative. Alright, now if you should find the Laplace of y prime, you are going to have s y of s minus y prime y of 0, right? So this is what we are going to have as the answer to the Laplace of this derivative. Now the last but not the least on that function will be the Laplace of 6y. So the Laplace of this 6y, as usual, the 6 can come out of the Laplace, which is 6 Laplace of y. And 6 Laplace of y is equal to 6y of x. So this is what we have. So as we've found the Laplace of each of these functions, the next step we have to do is to impute these values back to the Laplace. Right? If you impute the values back to the Laplace, what we are going to have will be, so before I impute, do the imputation. So as usual from what I did from the first video, from the first example as well. So I'll just say let y of s equals y, right? Let y of s equals y. Now let's go. So what we have is s squared of y minus s y of 0 minus y prime of 0. Alright. Minus. So I'm done with my y prime. So I'm done with my y prime. I'm entering my y prime now. But remember that there was a negative multiplying the y prime. So that negative will multiply these functions, right? So negative minus y minus s of this gives me minus s of y, because I say let y of s equals y. So I have minus s of y. Now minus into minus gives me plus. So I have plus y of 0. Alright. As usual again, I have a negative multiplying the 6y. So the negative is going to multiply this. So I have minus 6y, which is now equal to 0. Alright, because of course if you find the Laplace of 0, you are going to have 0. Okay? So that's why I have 0 here. Now let's go. So the next step you are going to do is to impute the initial conditions back to this Laplace. So just impute all your initial conditions back to the Laplace. So by imputation now, what we have is s squared of y minus s into, so what is the y of 0? Y of 0 here is 1. So I have 1 minus y prime of, minus, what is y prime? Y prime is minus 1. So minus 1 minus sy plus, what is y of 0? 1 minus 6y is equals to 0. Alright, so we have s squared of y minus s plus 1 minus s of y plus 1 minus 6y is equals to 0. So when you have this, all the function that does not contain y, should be taken over to the right hand side, while the functions that have y in them should remain on the left hand side. So if that is the case, what I have here will now be s squared of y minus s of y minus 6y will now be equal to s minus 1 minus 1. So this is what I have. And since this is the case now, I can decide on my left hand side to factor out y. So if I factor out y on my left hand side, what I'm going to have is y into s squared minus s minus 6 is now equal to s minus 2, right? So this is what I'm going to have. It's going to be s minus 2. Alright, so as usual, we are going to divide both sides by s squared minus s minus 6. So if you divide both sides by s squared minus x minus 6, we are going to have that y now will be equal to s minus 2 divided by s squared minus s minus 6. So, since we have this now, what we are going to do is to as well try to separate this function so that we can easily get the y of t that is present. Alright? So to do this now, looking at this denominator, we can factorize the denominator. Right? So if you factorize this denominator from what we have here, this clearly gives us, the factor of this clearly gives us s minus 3 and s plus 2. If you have s minus 3 and s plus 2, you can easily get back s squared minus 6 minus 6 minus s. Alright? So this is the factor of this function. Alright, so let's go. Now, when we impute this factor inside of this function now, what we are going to have is s minus 2 into s minus 3 and s plus 2. So, for easy identification, let me give you a recap on how to factorize this kind of quadratic expressions. Alright? So let's go through the factorization. So let's say that you have s squared minus s minus 6. To factor this out, what you do is to use the 6 and multiply the coefficients of the s squared. So what quotient of the s squared is here is 1. So if you multiply this by the quotient of the s squared, it will give us minus 6, right? If you use minus 6 to multiply the quotient of s here, s squared here, which is 1, is going to have minus 6. So your idea now will be, what are the two factors of minus 6 that when you, okay, write down the factor first. So the factors of minus 6 are, the factors are 1, 2, 3, and 6, minus 1, minus 2, minus 3, and minus 6. These are the factors of 6, right? So among these numbers which you've written, we are going to pick out two numbers that when you multiply those two numbers, they are going to give you minus 6. And when you add those two numbers or subtract those two numbers, they are going to give you the coefficient of this middle term. So the coefficient of this middle term is minus 1, right? Because minus 1 is in front of this s. So which number are we going to add together from here that will give us minus 6? And when we add those two numbers, it gives us minus 1. So clearly, we can see that if we should multiply minus 3 and positive 2, minus 3 and positive 2, okay, if you multiply minus 3 and positive 2, it's going to give us the minus 6, and if you should add them, minus 3 and positive 2, minus 3 plus positive 2 is going to give us minus 1, which clarifies this answer. So if that is the case, we are going to use these two numbers to replace the middle term. So this becomes s squared minus 3s plus 2s minus 6, right? So the idea of that number is just to replace it with the middle term. So when you have that now, what you do is to separate the two sides. So between these two and between these two, let's factor out. So what is here and what is here? So what you have here is s. So if I bring out s, I have s minus 3 on my first bracket. And on this second bracket now, what does this have and this have? Of course, it has 2. So if I should bring out 2, I have s minus 3. So since I have s minus 3 and s minus 3, I'm going to pick one of the box. So that means s minus 3. And of course, I'm going to have s plus 2. S plus 2. So this was how I ended up getting the factor of this function. Alright? So that's how I got it. So now let's continue. So since you have arrived at that function now, so what you are going to do as usual is to equate this to a over the first denominator, which is s minus 3, plus b into the second one, which is s plus 2 as your partial fraction, right? So since you have gotten that, the next thing you are going to do is to say let s if okay, first of all multiply this by this and multiply this by this, right? So we have a into s plus 2 and b, a into s plus 2 and b into s minus 3, right? Which is equal to the numerator of this function. Now which is equal to s minus 2. Alright, so from here now if you let s equals minus 2, if you let s equal to minus 2 from here, you can clearly see that we will be able to eliminate the a part of it, right? So s minus 2 gives a 0, and what we are left with is b of minus 2 minus 3, which is equal to minus 2, right? So let's continue now. When you have this, it becomes minus 2 minus 3 gives us minus 5, right? We have minus 5 into minus 4. So you have minus 5 into minus 4. So when you have that now, b times minus 5 gives us minus 5b, which is equal to minus 4. So of course the minus can cancel the minus, which ends up giving us b equals 4 over 5. So the value of b here is 4 over 5. Have that in mind. Now the next we are going to do is to let s equals positive 3. So if you let s equals positive 3, it's going to eliminate this b part to be 0, right? Alright, so now let's continue. So we are going to have a into 3 plus 2, wherever you see s, replace it with 3, which is now equals to 3 minus 2. So 3 plus 2, which is 5 now, gives us a into 5 is equals to 1, because 3 minus 2 gives us 1. Alright, so a times 5 gives us 5a, which is equals to 1. And from here, a is equals to 1 over 5. Right? A is equals to 1 over 5. So since we have arrived at this, so what we are going to do is to impute this back to this function, right? So we know that y of s minus 2 divided by s squared minus s minus 6 is equals to a. And a is equals to 1 over 5, right? 1 over 5. A is equals to 1 over 5 into s minus 3. S minus 3. Plus b is equals to 4 over 5. 4 over 5 into s plus 2. S plus 2. So this is the answer to this function. So now, for you to get the y of t now, for you to have the y of t, right? For you to have the y of t. So what I'm going to do is, as usual, is to get what type of function, what type of f of t from the first video reflecting this type of functions. So if you can think back, as when I got the how to find the inverse Laplace transform, because when doing the transformation, when you are trying to solve the ordinary differential equation using the Laplace transform, what you end up doing is to use the inverse Laplace transform at the end of the answer, right? So having that in mind, so let's find the inverse of this and this. Let's see what the answer gives us, right? Alright, so before I find the y of t, let's find each of them. So I told you when I explained the inverse Laplace transform, always factor out the denominator, right? So if you factor the denominator, I want to take each of these functions one after the other. So for the first one, I have 1 over 5 into 1 over s minus 3. So looking at this now, since I have 1 over s minus 3, which type of function gives us this? As you can see, this clearly gives us the exponent of 3t, right? The exponent of 3t. So since 1 over 5 is outside, this should give us 1 over 5 exponent of 3t. Now on the other hand, we can factor out 4 over 5. Alright, so from what I explained earlier, I told you not to, for safe reasons, that I should factor out the denominator first. But looking at this function now, I can't see a connection between the numerator and this function. Are you there? So since there is no connection here, I can just factor out the 4 outside, right? So I have 1 over s plus 2. And this clearly gives me 4 over 5 exponent of minus 2t. So hence, the y of t, which is the final answer of this function, gives us 1 over 5 exponent of 3t plus 4 over 5 exponent of minus 2t. Alright, so this is the answer to this function. This is the answer to this function. So I hope this video was useful and helpful. Please remember to like, subscribe, and share. Thank you.